Uh, Hello everyone, welcome back. Let's go to our third lecture. So last class, what we did was we went through these nice criteria, one by Harris and the other by Inrema, where the first one asked when random mass is a relevant perturbation. And we concluded by simple arguments that whenever d nu greater than 2, whenever this inequality is violated, random mass disorder is perturbatively relevant. Meaning that if your system is undergoing a transition and your system is somehow in the influence of impurities, quenched disorder impurities, static impurities, or inhomogeneities, the critical theory is unstable. So the transition will not be that of the clean system, will be something else. And today we're going to see one of those examples, one example where something else happened. Also, last class we asked when random field is relevant. Random mass, it changed the universality class of the transition whenever this is violated. But random field is even more dramatic. It enhances the lower critical dimension of the problem. So for discrete symmetry, in the clean case, the lower critical dimension is 1, it enhances to 2. And in continuous case, continuous symmetry problems, like Heisenberg magnets, the lower critical dimension is 2 and is enhanced to 4. Meaning that it can even destroy the transition. There is no transition at all. So it can be even more critical. So today afternoon, the colloquium will be about this topic here. Okay, so today class, we're gonna do the next question that whenever disorder is relevant, what can happen? Well, it can happen two things. The new critical point that arise can be classified as of a finite disorder character, meaning that it doesn't change much the character of the observables, nothing, those singularities that we have seen in the clean case will not change much. Just some exponents will change. But something else can happen as well. The transition can be governed by a theory that has infinite disorder character. And that's the case that I'm going to present today, now. So to see what means infinite disorder means that the singularities change mostly completely. One of those exponents that of the clean theory that was around 1 now can be infinite. So how can an exponent be infinite? Right? I'm going to see that. All right. So the model that I'm going to use is a toy model. I'm not claiming any experimental relevance. Also, we have seen that this type of theory can be applied to some experiments, but I'm not going through that. So this is a simple model that we can understand some physics. So I'm going to look at the quantum phase transition of this model. The quantum phase transition, as we discussed before, is between is a competition between interactions that want to align all the spins if this J is positive, and quantum fluctuations that want to flip these spins because this operator does not commute with that one. And I'm considering this other case, meaning that these couplings here, they are random variables. As we have seen before, this leads to random mass. And also this one. This also is random mass. It's not random field because I'm not putting the conjugate field of the other parameter, which would be a longitudinal field along Z. If I put this guy here, be I sigma IZ, this would be random field because it breaks the symmetry between up and down. This does not break that. If I increase H, I'm just saying that I need a larger H to have ferromagnetism, means it's random mass. So let's not deal with random field, just random mass. Yeah, then I wouldn't have this term here. If I want random mass, I would just put J's here, random. So the traditional approach, I told you yesterday, usually people, the old ways, you could do replicas, solve the clean system, treat disorder perturbatively by integrating it and using Gaussian integration and so on and so. But this approach fails badly, or miserably, or magnificently. Because the transition is governed by a theory that has a strong, actually infinite disorder character. So once we know that, then we have to think out of the box and think of a different approach, which we call nowadays a strong disorder approach that use disorder to actually simplify the problem. So I'll introduce to you this strong disorder normalization group technique. I don't want to deal with renormalization group details and the technicalities. I just want to keep it as physical as possible or intuitive as possible. I don't want to go into jargons, flows, fixed points, and all of that. Just want you to focus on physics. So the procedure is the following. We identify omega, which is the maximum energy scale of the problem. We have J's and fields. Those are the energy scales. And we identify the largest one in the chain. All right, that's easy. Go then search. Then we will say that this energy scale is much bigger than all of the others. It's assumption. Doesn't have to be. You can have J's that are narrowly distributed, fields that is narrowly distributed, and this is a bad assumption. But this treatment here fails badly, so I will go all the way around and assume that this local energy scale is much bigger than the neighboring energy scales. Okay, and then if I assume that, meaning that I'm using this order to simplify the problem, this statement will be very clear in a moment. I have to renormalize the system, and then we're gonna see what means renormalize the system. But once you do that, you have a new system now, and then you go back to A, and do everything again, until something magically or hopefully pray to your God and something magically happen and then you make sense of something. Because this procedure a priori doesn't tell you that you are simplifying the problem. You're just doing something that you think is physically intuitive. So let's see what is this thing that we are going to do here that is intuitively has a physical intuition, and maybe we can make some sense of the problem. Questions so far? All right. So B1. let's say that that large end scale is a field at site 2. So I'm using now the assumption that this field is very big, much bigger than the coupling, the neighboring couplings and the neighboring fields or whatever else. I'm assuming that. So if that's the case, the spin at that site too, they mostly will be aligned with the field. Especially if we are interested in very low temperatures. Since I'm interested in a quantum phase transition, I'm interested in very low temperatures. So a spin in a field in the x direction has two states. One aligned with the that field, one counter-aligned, and there is an energy gap between them. And I'm saying that maybe my thermal energy KBT is much less than H2. So I cannot thermally excite this spin. So mostly it's in ground state, the local ground state. So I will treat the rest of the Hamiltonian perturbatively. So in first order, I have nothing. Because the perturbation is sigma z in site 2, in spin 2. And sigma z flips the direction of sigma x, sigma z. Well, that's the Pauli matrix. I suppose you did Vitor's yesterday homework. There were lots of these Pauli matrices around. And if you act sigma z on one of the eigenstates of sigma x, you get the other eigenstate. So the average value of the perturbation in the ground state is 0, meaning that there is no correction to first order. Then you have to go to next order in perturbation theory. And also, as a homework of Vitor yesterday, you have to go through second order perturbation theory, so you all know what happens, right? So you need to compute these sort of mean values. So here is the ground state. Then you have H1, so you have the excited state, H1, ground state back, divide by energy of the ground state minus the energy of the excited state, and sum over the excited state different from the ground state. Right? And from this structure, we see what's going to happen. H1 brings the ground state to the excited state. So you get J1, sigma 1, sigma J2, sigma 3, and the same thing here. So this is square. So there will be J1 square, sigma 1 square, which is 1, because sigma z twice is 1. So it's a constant. The same thing here. There is a constant. And there will be the crossing terms. The cross terms is J1, J2, sigma 1, sigma 3. So there will be a constant that I will not care about. But there will be J1, J3, sigma 1z, sigma 3z. And of course, there is a 2, because two crossing terms, but there is a 2 in the gap, the energy difference. So the 2 cancels out, and I get in the bottom only H2. So if I look at this structure, I'm seeing an effective interaction between 1 and 3. And this is the effective coupling constant, giving parameterize this interaction. So actually what we have done here is somewhat eliminate the sigma 2 degrees of freedom, the spin 2 degrees of freedom, and renormalize the chain. That's what I mean by renormalize. So what I'm doing schematically is like this. I have 3 spins, one field that is very strong, and I have a J1, J2 here. And what I'm doing is I'm erasing this guy And now I'm coupling the neighboring guys by a different coupling called J tilde. And I have a spin one here. The H1, the H3 stays there. They were already here, they are not touched. And this J tilde is given by this formula here. J1, J3 over J1, J2, sorry. J1, J2 over H2. All right? Now I have a problem that has 1 degree of freedom less and different energy constants. Because now I have a different field. Coupling. I don't have J1 anymore. I don't have J2 anymore. I have now instead J tilde. And I don't have H2 anymore. All right? I have to keep doing that. Well, that's one possibility. I have a new system that is still like that one, but has different J's. Okay, so what happened when the coupling is the largest energy scale? The treatment's the same. We can already say what is the renormalization step by duality. But I will not claim duality here. I'll go a little bit slow. So B2 omega is J2, for instance. Meaning that I have spins 1, 2, 3, and 4. And my strongest coupling is J2. And I have fields H2, H3, H1, and H4. And J1 and J3. So again, I assume B, meaning that J2 is bigger than anything. So I will consider this as my unperturbed Hamiltonian, and the perturbation is simply all right. So diagonalize this guy. It's very simple. We have two energy levels. They are doubly degenerate. I have the energy level up, up, and down, down. And the other energy level is the other way around, up, down, down, up. And the energy gap is again 2J2. Right? That's for H naught. Now H1. What H1 is going to do here? This guy, well, at first, let's see. In first order of perturbation theory, sigma 2 applied here, it flips one of the spins. So it gets out of the degenerate manifold. So in first order perturbation theory, it gets 0, right? Because when I'm going to do the sandwich with either this state or this state, 0. And same thing for sigma 3. It flips one of the spins, which leads either this or that to one of those above. So in first order perturbation theory, no correction. Yes? Yes. Oh, sorry. H2. Yeah, H3. Thanks. Sorry? Side 2 is out of the game. We call that side 2 is decimated. No. Now I have a different game. This side 2 is not that side 2. It's just whatever is left, because now you remove side 2, then you rename it. Your chain goes from 1 to L minus 1 now. So in first order, it goes to 0. And second order is the same way, the same game. So sigma 2, when applied twice, it flips one of the spins, go up, and apply again, it comes back, right? So if I apply sigma 2 twice, I go and come back. Sigma 3, I go and come back. So this is a constant, because I always come back to the same state. So they will be in second order. H effective. I should write that Hamiltonian as an effective Hamiltonian, right? This is our H effective Hamiltonian. The constant, we can forget about it for our purpose now. But the effective H will be, again, a constant when applied twice, these guys. But the cross term is more interesting, because you go, for instance, if I apply sigma 2 in this case, in this guy here, I flip down, so down, up, I go here. And then I apply sigma 3. Sigma 3, I erase, I flip this guy and come here. So I'm mixing these two levels. So the degeneracy will be lifted. So you can see that there is a term that will connect this to that, right? But before saying the structure of this Hamiltonian, let me think of the following. What we have here, again, if my KBT is much less than the coupling, I'm throwing away these degrees of freedom, right? That's why I'm trying. That's what perturbation theory is. It projects this part of the Hamiltonian onto that manifold, the degenerate manifold. So what this projection means that we are integrating out of simply throwing away these degrees of freedom up here. So I have 4 states and I'm keeping 2. How can I represent 2 states? It's a spin health system. And see that this guy here, the 2 spins are aligned, always aligned. They are always up or always down. If I know one, I know the other. So actually, I will replace sigma 2 and sigma 3 by a single effective spin, right? So this new effective degree of freedom, this new spin, if it's up, it means that both sigma 2 and 3 are up. And if this new degree of freedom is down, both are down. All right? Okay. So if you do your calculation, you're going to see that you get a constant minus effective number. And you get this number here, 0, 1, 1, 0. That's your effective Hamiltonian. And this constant is simply H2, H3 over J2. And this operator here resembles what? Resembles sigma x. So this is minus H2 sigma tilde x. That's our effective Hamiltonian. All right, from where this constant comes from? I applied H2 here. It goes up there. And then I applied H3 to come back. So it connects the state up, because here is up, up, and here is down, down. So to connect the up, up with the down, down, I have this term here. So I applied H2, H3, and of course, the second order perturbation theory, I need the energy difference, so I get a J2. It is the degenerate perturbation theory. That's why I have two ground states, right? I have this ground state and that ground state. Mm-hmm. Yeah, first order gives you 0. Yeah, I have, yeah, that's right. So I have ground state I, and I have ground state J. So this is 0 for I and J. So I goes from 1 to 2, and so is J. 1 is here, 2 is here. So all matrix elements are 0. You can say that 0, 0, 0, 0. The second order, then you get a constant, which I put here, but you get a mixing of these states. And that's the important part, yeah. Yeah, that's, I'm going to, yeah, it's, since the effective Hill space is the same as spin half, so it is a spin half for all purpose you wish. But of course, this degree of freedom represent two spins that are aligned. So if this degree of freedom is up, means that two spins are up. So the magnetic moment of this new degree of freedom is the sum of the magnetic moments of the previous spins. So we need a new degree, we need to specify that, meaning that the magnetic moment of this new degree of freedom is actually the magnetic moment, the sum of the other magnetic moment, the decimated degrees of freedom, the magnetic moment of sigma 2 and sigma 3. All right? Because if it aligns, means that two spins are aligned, and so on. So schematically, what we are doing, we are fusing these two spins together. Well, that's what J does, right? The ferromagnetic interaction. It wants them to align. So it's a single degree of freedom. So meaning that I'm replacing these two spins by a single spin. So it's a bigger spin, meaning that larger the radius of these sites, larger the magnetic moment. But now I have a effective coupling there, and the remaining ones just remains the same. H1, H4, J1, J3. And this new effective transverse field, because it's also transverse field, is given by this equation. All right, very neat. So again, I have, after I did this procedure, I have 1 degree of freedom less than before. Because I removed 2 and I put 1. And in that case, I just removed 1. Very intuitive or not? What do you think? I'm using this order in my favor, right, to do these simple perturbation steps. Because perturbation theory, it works if these constants here are much smaller than the original one, yes. Yeah, you can do that. And you have new normalizations. Yeah. But I'm not going to do that. It's boring. Yes. Because you remove out of the criticality, right? Yes. Okay. I can. All right. So we have. Is there more questions? We have we can put here as a mu2 the mu1, mu4 if you want. We have everything that we could have done in step B. Now you go to step C. Says that we have to go back to step A and repeat it until something happens. But what's happening with this procedure? Suppose I have a distribution here of P of J, and the distribution, I don't know, let's say R of H. What's going to happen in this case? Well, step A, identify the largest coupling, which is right here. And then I have to do step B1, meaning that I have to remove J1 and J2 from the distribution. Let's say that J1 is here, J2 is there, and that this is the H I'm removing. So I have to remove them from the game. And what I have to do, I have to insert a new coupling in J. Where is this new coupling? Since H2 is bigger than J1, J2, the new coupling is smaller than the smallest of them. So it has to be to the left of this guy here. Maybe here. I have to insert it there. And then I have to keep doing this, right? Then I cut off this distribution. It's a little bit less now. And then I remove the next one. I remove the next ones. And I put the next one, and so on. So I'm changing the distribution of these couplings. And if I have this initial configuration, meaning all fields are bigger than all the couplings, what's going to happen? It's going to happen that the fields will just be cut off. So in the very end, I will have a very narrow distribution of fields here. And what happens to the J? The J just keeps getting smaller and smaller. Then I have lots of J's that are here. A very steep and singular distribution of J's. A huge weight in zero. What's that? Well, I have a new effective Hamiltonian where all these couplings are much smaller than all the fields, the transverse fields. This is a simple paramagnet. I can just erase this guy here, and I get a simple paramagnet. Okay, so that's one phase. That's one possibility that can happen. I could have the other way around. I could have here the H, so RH, and I could have here the fields, PJ and J. So I would have the other way around. I would have very weak fields and very strong couplings. And this is the simple ferromagnet. So if I'm doing this procedure, at least I can make sense of the deep ferromagnet, deep paramagnet, which is actually a trivial, right, statement, because if all the J's are stronger than all the fields and the other way around, we know what should happen. But at least this is consistent. What becomes interesting is when these two distributions overlap. Right? At some point, there will be a transition. We know that if one is here, we have the paramagnetic phase, and the other is the ferromagnetic phase. So at some point, something will happen. Right? So how do you analyze the problem? Especially, let's say that the distribution of J is equal to the distribution of H, the initial distribution. If they are equal initially, this has to be preserved through this procedure. This is called conserved under renormalization group flow. Why this has to be conserved? Because the J's are renormalized the same way as the H's. So there is no reason why one has to win or not. So when this happens, we know for certain that this is the critical point, because neither H, neither J, nor J win. Both stay together all the way around, and that's the critical point. So that's the transition. All right? But how do we now know what happens to the distributions? And then there is a mathematical way to see how these distributions change. You want me to deduce it or just give you the result? So that means that you want to really want to deduce it? Okay, let's go. You're not going home. All right. Yeah. Sorry, what? Yes, okay, good question. This procedure that I'm using here, I'm always saying that this is a random variable, and treating this guy here as other independent random variable. And this means that when I pick up one of the fields here, I can pick up the J's anywhere here. This means that these random variables are independent, and this was the assumption. So that's why I can do this, at least at the beginning. Of course, you can inquire later, after you did many times this step, if this remains true. Because if it does not remain true, it means that if I pick up a large H here, I cannot pick up any J here. I have to pick up the J that is near to that H. So it means correlation, spatial correlations between these other variables. This procedure can be done even if these random variables are correlated. I just know, I just pick up in the chain, I keep track where are all the J's, where are all the fields, and I keep doing that. But if they are correlated, it doesn't mean that I can write down a simple equation for that. The simple equation that I'm going to write here, I will assume that it is independent, so I can remove anywhere here. But the procedure can be done even if they are correlated. And actually, André does that a lot, because he works with this method with perfect correlated variables. It's aperiodic. It's not a random disorder, it's a periodic disorder. And through Monte Carlo simulations and other reasons, we know that these work. But you cannot write down the equations that I will write down right now. Okay? So let's, and we know that they remain independent. Why? Because this new field here has nothing to do with J1, J3, right? I have a new random variable that is statistically independent from J1, J3, or everything that remained before, after the decimation, sorry. So H tilde, J1, J3 has H1 and H4 has nothing to do with each other. So this procedure guarantees that if the random variables are independent in the beginning, they will remain independent. Okay. So let's start. So I have, let's say, I have R of H, J, and P of J. And let's say that they have the same, well, this is our cutoff. H now is the maximum of J's and fields, and this is a cutoff. Maybe I drew, they are not equal, okay? They are not meant to be equal. I'm just drawing two different functions here. Okay, so I will do this procedure in the following way. I want to know, now I'm going to say that the Pj is a function of the J and omega, and the same for the H. They cannot, omega means the maximum value of this distribution can have. Now I want to change H omega to omega minus d omega. So this is d omega. And I will make the omega to infinitesimal, so it's 0. But I will remove all the fields that are here and all the couplings that are here. All right? So let's see what happens to Pj, J omega minus d omega. So this is certainly P of J at omega. I will put some number here that I will tell you later what it is. When I remove, when I diminish omega from to omega minus d omega, what happened? Well, this distribution of J remains the same up to something that I will change now. Right, so P of J omega is P of J omega, omega minus d omega is that. But when I remove these couplings here, what happens to the function P? Nothing, it's just cut off. Up to some normalization now, because now this distribution is not normalized anymore. So I will put the normalization here. So how much is this normalization? We know how much is that, right? Because we remove this area. How much is this area? This area is P omega d omega. This is the integral of P between here and there, and this gives that. If I make the omega to 0. So it would be 1 minus P omega d omega. Yes, omega, omega. So nothing happens, that's it. But of course, I'm decimating also the fields. So what happened when I decimate the fields? Well, I remove two of those guys here and put one there. So in terms of area, what have changed? Well, I remove one area here. This area is equal to this area. How much is this area? This is R omega, omega d omega. So I remove this area, and put this area. So I remove 2 and put 1, so it's minus R omega, omega d omega. What else? Well, I didn't remove everywhere, right? And I have to remove now J1, remove J2, and put J tilde. I have to do that. How do I do this? Well, I'm removing. So P of J omega minus D omega is minus something. What is this something? It's a functional, right? Because I'm changing a function. So I will write down the following. So this is R omega, omega d omega. It has to be proportional to d omega because it's an infinitesimal change. And I'm integrating of all possibilities. So what's this? This is the probability of having a field decimation. So I'm decimating the field, so that's why it's R omega, right? The probability of decimating these fields here. And that this is the probability times Pj1, Pj2. And that this is the probability of having J1 and J2 around the field that was decimated. So this is the probability of finding this link here. These three numbers. And of course, I'm summing over all possibilities of J1 and J2. That's why I need independent random variables. Otherwise, I couldn't do that. Okay. So what I have to do now? I have to remove J1. I have to remove J2. So I remove it. The minus is right here, so I don't need the minus anymore. J minus J1. So one of the couplings I'm removing. I have to remove J2. And I have to insert J tilde. But how much is J tilde? So I have to insert is a plus. There is a minus here, so I put another minus, I get a plus. J minus J tilde. What's J tilde? I can erase here and put its value. That is J1, J2 over H2. But H2 is the maximum, right? Is omega. This is 2 omega. So I put omega here. And that's my equation for the P of J. So I need another equation for R of H, which is the same as this one, but with J and H exchanged because of duality of the procedure. Oh, this is normalization. Okay, so now if I integrate from this P of J omega, it has support between 0 and omega minus d omega. And it has to integrate 1, right? If I integrate P dj here, right? So this integrate 1, this does not depend on J, this is just a number. So since it is integrated to 1, the result of this integration is this, right? But now if I integrate from the, also I have to integrate from to the left side, dj from 0 to omega minus d omega. What should I have? I needed this, well, this integrated to 1, but I'm not integrated up to omega, but omega to minus the omega. So this is 1 minus P of j d of j, which is this number here. So this is already 1 minus this number here. And this other number is what? Well, I have delta functions. So I get this cancels to that, and I get 1, I integrate over j, one of this guy goes away. Another this, well, I have integrate on P of j, and I get this one here. Because I'm integrate over j, right? So that's the normalization. It's a bit technical, but you asked for it. Andrea warned you. But we are done, right? Now you can simplify. Because the delta integrals are easy, and they get 2 equations. And of course, things you simplify of the following. P of j omega, this is P j omega minus dp d omega, right? This guy here. So I have a pj, which multiplies by 1, which cancels this pj. So I get everything, I get the omega with the omega square, you forget about it. So I get minus p omega times 1 d omega, and that's it. So this d omega cancels this d omega. I integrate over 1 of the j, so I get a p of j. The remaining thing is the following. I get, so I don't get any mess up signs. Get something like this. This minus 2 is because of these 2 delta integrals here, right? Now you can simplify things. And I will write down for minus the r d omega equal r omega omega. Oh, I forgot some term here. There is also plus. This term here comes from the normalization, right? Because I get P of j multiplying these guys here. And I pass to the side, so you get a plus. So you're going to see that I have R and P, and I have R and P, but with a different sign, so we get a minus 1 there. And I get a P and P, which when you simplify, you get something like this. Not, okay. So I have 2 equations. which are integral differential equations. They are nonlinear. No, okay. Yeah, they are nonlinear because there is p inside the integral, and yeah, that's there is p and r here. There's integration. There is differentiation. I suppose these sort of equation, they appear in 79 when some gentlemen invented this method. But only in 92 they were really understood and solved. To solve it requires lots of calculations and assumptions, and then we will not go home. I will for weeks. But since I know the solution, I will put it here in these equations, and then we're going to see what happened. Yes. Sorry? Here is R omega, 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 and also omega, omega. Here's R. Yes. Because I'm writing now the other equation. Yeah, sorry, I did a step. If I simplify this one here, I will end up with this equation with R exchanged by P and J exchanged by J. I'll just simplify, right? That is, then you get this minus. You see, I get PP, so I get, I I forgot some number there. Even copying it, you do mistakes. Yes, thanks. That's why I was missing. All right. So much for this technicality. Not much of physics here. But soon we come back to physics. It's very convenient to introduce these new variables. These are log variables. Why they are interesting? Because the renormalizations are all products. You get JJ over field, and you get field over coupling. So if I introduce log variables, these transformations become linear, become sums. And that term in the flow equation, this is called flow equations, this term here becomes a convolution. Because now you get probability of, called beta, right? Beta, beta, and then you get the beta minus beta 1 minus beta 2. And convolution, it's a better way to work with it, with that. But let me just say what's going to happen to the four equations. So let me say that P of J dj is equal to P tilde of Z dz and RH. And now the four equations become that. All right, where so this guy here, 0 is when H equal omega, then beta is 0. Omega I is the initial coupling of your system. So you have the initial J, initial field, and the initial maximum value of J in field is omega I. Just that. Usually set to 1, because let's say that the distributions of J's and fields are distributed between 0 and 1. So this would be 1. And the distribution of couplings and the fields will always remain distributed between 0 and 1. In these log variables, they are distributed between 0 and infinite. When J is equal omega, you get 1, but when J goes to 0, this goes to infinite. All right. Yes, that's right. Thank you. How much time do I have? It goes until? Okay. Yeah. No, this is R. Yeah. All right. So I will show you what the solution of those equations are. And the solutions are the following. I will not draw the tildes anymore. For now, I remove the tildes. P of zeta is P naught E2 minus P naught Z. So that's our distributions. So they have these numbers here that depends on gamma, on the cutoff, but the only dependence on the J's and the fields are in the exponential. So the solutions of these equations are exponential. Simple exponential, it's kind of easy to see because to satisfy this convolution, you need exponential. It's not easy to see, but get this thing here, put there, you see that's correct. Thanks. All right, so if you put these equations to our flow equations, then what happened? Then you're gonna see what these functions of a gamma, P naught and R naught has to be. So there will be a differential equation for those constants, or for those functions. And those equations are That's it. Okay. So you can see the following. What mean constant of the flow? A constant of these equations here. If I say dd gamma of P naught minus R naught, this is 0. Right? If I subtract this equation from this equation, I get that. Meaning that P naught minus R naught is a constant of the flow. What's this constant of the flow here? You see that I get a zeta here. So if I would like to know what's the mean value of zeta, what's this? Is 1 over P naught, right? The mean value of beta, 1 over R naught. But the mean value of zeta is the mean value of log of omega minus log of j. So is that the mean value? The mean value of the log. And the same here. So at criticality, when we know that critical point happens for sure when the distributions are the same. We discussed that. If the distributions are initially the same, means that R naught equal P naught. And the difference doesn't change along the flow. So R naught equal P naught is the critical point. Right? Everybody can see that? As we could require by duality of the procedure, right? Critical point, R naught equal P naught. Meaning that this constant is 0. But this means what? That along the flow, the mean value of the logs of j's will always be the mean value of the logs of b's. Meaning that in the beginning, this is also true because it's true all along the decimation. So the critical point means that log of j equal log of h. So we discovered that critical point. And that this is true exactly in this model by duality. And there was some work by Feti that work out properties of tridiagonal matrices. Tridiagonal matrices, they appear in this problem because it can be mapped into free fermions, as Fernando was saying in the first class. And that tridiagonal matrix has a 0 eigenenergy, meaning that you have a gapless state when the log of the field is equal to the logs of j's. So that's the critical point. All right? It is in the initial state, in the initial j's and fields, and it remains throughout the okay. Now we can try to do some physics, come back to physics, since we know the critical point. But then you can inquire me, how can we do some physics? We started from the transverse field easy model, and we still have the transverse field easy model, but with different couplings and different fields. So how do we still solve the problem? Well, it comes from the solution of this equation here. Let's solve it for the critical point. What's the, for the critical point, what's our equation? dP naught d gamma is equal to minus P naught square. Meaning that P naught is 1 over gamma. So the critical point, or the critical distribution, P of zeta, Land puts a star here to say that's the critical point. This is 1 over gamma, exponential of minus Z over gamma. So it's a distribution that is like that. So I have Z here, I have a P of Z, it's 1, 0, and has width gamma. This means that the typical value of Z is increasing when we diminish the energy scale, because when I diminish the energy scale, when I put omega to 0, this goes to infinite. So you have a distribution that is infinitely broad, even in log scale. Think of a distribution that you like. I like box distribution, don't know, between 0.5 and 1. Take the log. It becomes even narrow, right? It's not this distribution. I can reverse back, right? I can come back to the P of J, and the P of J's is something like this. So P star of J. Will I remember the prefactor? Well, I always say that's proportional to 1 over J to 1 minus 1 over gamma. So it's extremely singular distribution because gamma is going to infinite, this is going to 0, this is 1 over J. It's barely normalizable. This exponent here that is just above 0 is the thing that makes this distribution normalizable. So I have a J, a P of J, that is shooting up the sky there. Okay, so what? How does it help us to get the physics out of it? Joey, do we have exercise for that or not? Okay. So the physics comes out of this. You see that you have a very singular distribution when the energy scale is lowered. So you're going near the 0 temperature, near the ground state. So this ground state has very singular distribution of couplings and fields. So if I stop here, let's say the initial distribution was something between the J's were distributed between typical J's in magnets, let's say 1000 Kelvin, 500 Kelvin is the transition for iron. And we have some disorder, I don't know, this is 900 Kelvin. Well, doesn't matter much. And then I keep decimating until I arrive at 1 Kelvin. Very low temperature. Well, this should be omega is 1000, and 1 Kelvin now is 1, and you get 3, 1 over 3. This is a huge number, very singular. So let's say that I reach at this energy scale and I cannot do decimation anymore because now the excited states, the U omega is of order kBt. So I can stop now my procedure. So what helps? I still have a interacting problem, but it's barely interacting problem. Because the probability of a coupling that is much weaker than kBt is huge. Very few spins will have a coupling that is of order kBt. The great majority of them will have couplings and fields that are much, much, much weaker than kBt. So they are essentially free. And the free problem, we know how to solve it. All spins are free. I can compute magnetization, I can compute susceptibility, I can compute whatever I want. And that's how you use disorder to your favor. It's because if you compute j square minus j to the square divided by j, this goes to infinite as omega goes to 0. This is the concept of infinite randomness. I cannot, by any means, substitute the distribution, which is extremely broad, even in log scales, by a single coupling or a single energy scale. I have a huge spectrum of energy scales. And that's the concept of infinite randomness. That's why those other methods fails badly. So since I'm running out of time, I can show you some pictures. It's not that. What is this? Oh, okay, good. So that's what I told you before. Here's the phase diagram. You have a paramagnet to larger fields, a ferromagnet to smaller fields. That's how you do the decimation. Those are the calculations, the perturbation theory. That's degenerate perturbation theory, as we showed before. And well, here's duality. That's the duality transformation, so you can exchange interactions by fields. And that's the normalization procedure that was telling you. You identify omega, you remove it. If it's a j, you increase. It's a field, you remove, and keep doing that until something happens. And if you have started with this initial distribution, you flow to something else. That's evidently not the critical point, right? Because the critical point, they become equal. But that's the possible flows that I was telling you before. If all fields are greater than all the H's, you get a strong ferromagnet, and the other way around. Let's say, paramagnet. I call weak paramagnet, I don't know. It should be a strong paramagnet. And now, if they are more or less the same, meaning that the log of the field is equal to the log of j's, you flow to a universal distribution, and that's important. Doesn't matter from where I start. I could have something totally different from here, but if I'm at the criticality, I will always flow to this solution that I drew here. Doesn't matter where you come from. I did not show it here, but that's the result. So in some sense, disorder becomes universal because there is only one infinite. That's this distribution here. But if you are in the somewhat intermediate region, something interesting happens. Because here the fields and are stronger in majority than the couplings, but some of the couplings are bigger than the fields. So when you normalize these strong couplings, they will produce weak fields. So the support of the weight of the distribution of the fields will grow, and you have a weight at zero, a finite weight at zero. And so the other way around. And this is important. I will tell you why tomorrow. But just to summarize, if you compute the magnetization in the clean system, you get this result. Delta is the distance from criticality. Delta is the distance from 1 here in this case. But in our case, you get something that is totally different. I didn't show you how to do that yet. I hope to maybe finish this part tomorrow. Here's the 4 equations that we have discussed. That's the solutions. So what I was telling you, that doesn't matter from where you start, you always end up in the same point if you are at criticality. This means a universal fixed point distribution. That's the concept of infinite randomness I was just telling you here. So the mean value of the coupling is very different from the typical value of the couplings. And I will come back to this point tomorrow because I'm running out of time. All right, so I stop here. Yes? Narrow. It's becoming narrow because the system has a gap, right? Suppose it's initially here and you have something else here for the eights and for the fields, or the other way around, doesn't matter. The coupling is always here, so you are just decimating this guy and it's becoming narrow and narrow. That's not a problem. Your perturbation theory is becoming better and better at criticality. Why? Because as we have just discussed, the width of this coupling, of the distribution of couplings, is infinite. So as you approach the ground state, you are doing your perturbation theory, you get a large coupling that's right here. What's the probability of having a bad perturbation theory? It's the probability of having a field or coupling that is right here, but this probability is very small. The great majority is way up in the zero. Maybe I'm not drawing correctly, but maybe here you can see it, right? Because this is infinite, so it goes up here. So the probability of finding the one that are decimate is here at 0. So the probability to find a one that is very close to 0, it's going to 0 because we have that, right? Actually, this is 1 over gamma. So your perturbation theory becomes better and better. And it was conjectured that if what we have done here is correct, it is asymptotically correct. And it has been verified by many numerical studies that everything that we did here is indeed exact, asymptotic exact. And tomorrow I will compute some observables, and you see some huge difference. What I will focus the most, do I have it here? Yeah, I will focus the most in this phase, what called Griffith's phase around the critical point. Yeah. That's everything analytical here. That's the calculations that you have to do. It's not complicated at all. You can compute, for instance, susceptibility. That's how you compute susceptibility. You need this quantity that is the density of spins that were, for instance, how do you compute density, susceptibility? You stop your RG flow until the temperature you want, very low temperature. So everything else is free, as I just told you. The couplings are much smaller than the temperature. So each of those remaining or not decimated spins will contribute with a Curie term. So that's a Curie term. It's the momentum square over T. But the density of couplings, I know how is it because I keep track of everything. It's probably computed in the previous slide. It's computed here. And I also know how the magnetic moment behaves, which is, I don't know, maybe somewhere else here. Yeah, I don't know. But then you can compute the susceptibility as a function of temperature. The same thing as magnetization, so we need to put B that I said that was boring, but it's very easy to put B again. You can compute entropy because each of those remaining spins, they are free because temperature is so high, and each of those contribute with a log 2 to the entropy. So you just need to know the number of spins remaining, and that's the entropy, so you can compute specific heat and everything else. So we come back to that tomorrow. So indeed, we can use disorder to your favor and compute observables. Mm-hmm. Yes. You change the topology of your... this is not a problem conceptually. You can still do that, and people do that, and we get a nice result as well. You do have this physics in higher dimension. Actually, infinite randomness critical point for this model is infinite randomness in all dimensions. Even when it's a different Harris criterion that you have to apply because D infinite, you think that D nu is greater than 2. So it has some subtleties. So as infinite randomness is, for this model, happens in all dimensions. But the thing is, you cannot do this analytically anymore. But you can do numerically. And numerically, you see all these physics again. You just change a little bit one or other critical exponent, but everything remains the same. All right. So tomorrow we compute some observables and finish this thing here. We will focus on Griffith singularities, and I hope I promise you that the calculations will be much, much easier. There is a simple way to see Griffith singularities. And I'm sure you will be happy, not to be technicalities like today. Okay, guys, so we resume at 2 for the colloquium. See you then.